All right. So the first thing I want to look at, so problem one on project one basically is this. I took basically a modified version of the problem, all right, that I put together. Modified because the example circuit I'm going to do is similar but not the same. Okay. So here's the circuit on problem one. So basically what I do is I say, all right, this is modeling. So it's a timely problem, I guess. It's a modeling a situation where I have a tree that falls on a power line that was providing 10 kilowatts or approximately 10 kilowatts previously to a house. So this is circuit. This is what we really do with circuits for the most part. What do I have here? This basically is what? This is a house. This is what I'm saying. This is a house that is absorbing 10 kW of power, approximately 10 kW of power. And so this is, when we build circuits, they're models for what's happening electrically somewhere in the real world. So the house is what I have as my load. And then over here, this is basically a model for the power line. So this is basically a model for the cable that is, passing between two wooden poles out there, or many wooden poles out there. Okay. And then this is basically over here. This is, and I could think of this whole thing, I guess, if I want to. This whole thing is the grid, quote unquote. From the perspective of the house connected to the grid, it looks like what I showed right there. And in this case, I said that this voltage had an RMS value. So if you're in circuits 2, hopefully you know what that is. So RMS value of 480, and the frequency was 60 hertz. And I said it had some angle, right? I left it as a variable. Okay. So when I say that whole thing is a grid, just out of curiosity, what is that? What theorem did I use by calling the grid a voltage source and some stuff in series? What theorem do you know from circuits that I use to do that? Because first of all, let's be clear, the grid is not, the electrical grid is not a voltage source and an inductor and a resistor. That's not the electrical grid, right? What's the electrical grid? Well, it's thousands of miles of wires and many thousands of generators and all these kinds of transformers. It's a bunch of stuff. This is a model of it, right? So what is this model? What theorem did I use to make a model like that? We use it all the time. It's the only thing that allows us to do anything in the real world. What theorem did you learn in circuits 1, which allows me to simplify the entire power grid into that? What theorem did you learn in circuits? Let's go through. What theorems did you learn in circuits 1? KVL. KVL, that's good. KVL is one of the most important. KVL, KCL, Ohm's law. What? Exactly. Thevenin's theorem. Thevenin's theorem says I can take something that's endlessly complicated, like the electric grid, and I can reduce it to a voltage source in series with a resistance. Or more generally, I know not all of you are there yet, but basically a voltage source in series with what we call an impedance. All right. So this basically, this is what. So you think about it. Basically, there's a voltage source that's behind, effectively, from the perspective of the load. It's behind, the source is behind a wire. What's a wire always have? Wire always has some resistance, hopefully small. In this case, I said it was 0.1 ohms. Okay. And it also has some what? Inductance. Why does it have inductance? Why does a wire have inductance? Well, it's because current runs through it. So there's magnetic fields running around it. So there's got to be some inductance to it. So most of the time, you guys think of wires as wires, right? And they are until the inductance matters, right? That's the main thing about anything that we do. All that we ever do is really analyze models. When you guys analyze a circuit, you're analyzing a model. A resistor, like you go in the lab and get a resistor, that's not just a resistor. It's a resistor and it's got some inductance associated with it as well. But inductance only matters at certain frequencies. All right. So in other words, if I put a gigahertz into my circuit, it might behave differently than if I put 1 hertz into my circuit. There's a lot to that, but this is the type of modeling that we would do. So the other thing is I said this switch is modeling a tree falling next to the house that basically is taking that line and forcing it to short circuit the ground. Okay. So a line that basically falls down and hits the ground is basically creating a short circuit. There obviously is not somebody sitting next to the house throwing a switch so that I short circuit the grid, right? But that's a model for how we would think about it. Okay. So this is the type of thing that we would do in a lot of real world problems. There's a good case for where you would use a simulation typically to deal with this. And we'll let me actually talk about that now, because one thing I didn't include here, well, I guess I did. I included this point. I know that's super tiny for you guys, and the TVs are off. I don't know. I don't know if that's going to turn on all the displays. I don't know how to turn those things on. Probably would be helpful for you guys to see. Obviously you'll post this, but the last question here basically says, and I guess maybe to back up for a second. So what I'm saying here is what I do with this typically is I got to figure out a circuit breaker, right? What's a circuit breaker do? What's the job of a circuit breaker? You've heard of one, you've seen one, you've probably seen them flip. What's it do? It does what? It opens the circuit if I have a short circuit, right? So basically it's like a switch. So it's like let's say I had so a voltage source should typically be, let's say I have a 10 volt source with a 0.1 ohm resistor, and somehow that thing short circuits. How much current's going to flow in that circuit? If I have 10 volts and 0.1 ohms, how much current's going to flow? 100 amps, right? So if I had a 50 amp breaker, that breaker would be in series with that source, and the breaker would open because it sees that the current exceeds basically 50 amps, and it opens so that the current stops flowing. So it protects, right? The job of it is protection. So obviously, in the power grid, we have to have protection in the system. You don't want to have, a line short circuited to ground and the current just kind of pumping around, right? That would be bad, right? So what we do is we have a circuit breaker, which would be somewhere over here, basically a switch that will open up whenever what we call it a fault, whenever that fault happens, okay? So I got to choose that circuit breaker carefully, right? And when I say choose it carefully, what does that mean? What do you mean by choosing it carefully? What matters, probably? So in the example I just gave here, I said, well, if I have a short circuit here, I'm going to get 100 amps that flows, all right? How would I choose a circuit breaker? What would be the key thing I would need to know? How much load is on the circuit? Yeah, so if normally the circuit is expected to provide 20 amps, I know that if I'm providing 100, that's a lot more than I should be providing. So I probably want a breaker that's sized a little bit above that 20 amps. Okay, that's how we choose these things. So given that, right, I need to understand based on how much load. So this is my load over here. Based on that load, I need to know how to size the circuit breaker. So I can say basically over here, maybe normally I expect it to be 1 amp. And if it hits 100, well, that's way too much. I got to turn it off. All right. So basically, this is the type of thing I would need to do design. What would make that challenging, do you think? What would make it hard to actually figure out how to set up that breaker? I need to know how much current's going to flow in that short circuit condition. All right. I need to know how much I would normally have, right? And I need to know how much is going to happen in that, what I call that short circuit condition. So what's the hard part of that, do you think? What's hard with figuring out the short circuit current? Or the current that flows once that switch is closed? What's hard about figuring that out? As I showed you, it's not necessarily hard. There's a differential equation to solve, right? But that's not necessarily hard. What's hard? There's something that's actually kind of difficult. Any idea? Yeah. Well, finding the current passing through that resistor, what's hard about figuring out that current? There's an inductor and a resistor in that circuit. All right. If I told you it was a circuit that had a voltage source, an inductor, and a resistor, that I'm not calling that hard. Maybe you might find that to be hard because it's a harder problem to solve, right? I get that. That's not why I'm saying it's hard. The problem is, in your mind, you think of that, well, there's a 4.5 millihenry inductor and there's a 0.1 ohm resistor. That's a model for a wire, right? I don't really know if it's 4.5 milliohms or more millihenries, and I don't know if it's 0.1 ohms. And as soon as I get a lot of current going through that wire, what's going to happen to the resistance? It's going to pretty quickly go up, right? So I take a guess as to what that's going to be, right? And so no one really knows. If I give you a section of wire, that wire's inductance and its resistance are going to change over time. And so it's a guess. So an engineer doing design is probably going to not want to solve the differential equation 1,000 times. He's probably going to say, well, worst case, maybe it's this value. Best case, maybe it's this value. So somewhere in some range, right? So he's going to want to do sort of a series of analyses to figure out what's going to happen in a range, okay? And that happens a lot. There's a lot of cases where you do in real design, you don't really know what those values are. And there's things called codes and standards or whatever that kind of help you to make some guesses as to what those values should be. But given where you guys are in analysis mode in life right now, where you're learning how to solve stuff, where we just tell you the value is this and the value is that. In reality, we typically don't know that. It's a range of some kind. All right. All right. So enough about that, but this is the typical reason why you would want to do this type of a problem. So I want to basically solve something pretty similar. In this case, I ask you guys to be looking at this current. In this case, a similar circuit, except I want to solve for the voltage across the capacitor. Okay. And I've got a couple of resistors. I got 2 resistors here. All right. Now, what we're going to do is we're going to go through part A and B of this problem. Actually, I guess we're going to go through A, B, and C of this problem. So let's see. I know this is tiny, but it's basically the same as, I mean, I copied and pasted this from my Word document, so it's similar. So part A here, it says it's got a bunch of parts, and you guys are going to start laughing at some point because I have part A, and then there's a couple of parts underneath part A, and I make it structured, all right, which sometimes confuses you more. I get it. But I try to structure it, okay? So I basically say I want to determine the amplitude of the steady state voltage once the switch closes. All right, so forget about the rest of what I said there. We're going to parse that, but I say I want to determine the amplitude of the steady state voltage once the switch closes. That's part A. Okay. What is the circuit that I have once the switch closes? What is the circuit that I have once the switch closes? Yeah. Only going to have the source, the capacitor, and R1. That's right. So let's just make sure everybody's on the same page with that. So I know some of you guys are still thinking about circuits. I got this voltage source. I got R1. And basically I have this. All right. Once the switch closes, the switch is a short circuit. Why did he say I should remove R2? Why can I remove R2? Because it's shorted out. Because it's shorted out, right? So that's a memory device in your mind. The way I think about this is if you're in circuits 1, circuits 2, the way you should really think about that, I think, is if I do a KVL around this loop, right? If I do a KVL around that loop right there, Kirchhoff's voltage law, what's the sum of the voltages around a loop? Always 0, right? So the sum of the voltages is 0 around that loop. So that means I have 0 equals I times R2. What does I have to be? There's no current that can flow down this branch, all right, because of that reason. That's why, right? It's important for you guys to, so I'm glad somebody said KVL, right? Circuits, you can learn a bunch of stuff, right? You're really learning only 3 things: KVL, KCL, Ohm's law, nothing else, all right? That's really all you're learning. It feels like you're learning a lot of stuff. You're just basically applying those rules over and over and over again in different ways, all right? That's the important thing to remember there. So that turns this into this. All right. And my capacitor voltage is there, defined that way. All right. So what did I ask for? I said I wanted to determine the amplitude of the steady state voltage once the switch closes. So here's the circuit once the switch closes. How do I get the steady state voltage on that capacitor? What does that mean? Yeah. Basically, I know not all you guys have gone through this yet. I think it's fairly straightforward given the circuit's not hard. Basically, he's right. I got to get a differential equation, and then it's a math problem from there. Once I get the differential equation from the circuit, it's a math problem. So when I say the steady state solution, what am I talking about? Talking about the particular solution to the differential equation. All right, so I'm going to treat this. I think even if you're in circuits 1, you can handle this. All right, and the only thing that's different here is basically if I have a resistor and I say here's R, and I define the voltage on that resistor like that, and the current on the resistor like this, what's the relationship between V and I on that resistor as I defined it? What is that? You should know that. What's VR equal to for that resistor? Just I times R. Exactly. Not that complicated. IR times R. Now, what if I had made the current go out of the plus sign? What would have been different? It'd be yeah, VR equals negative I times R. So if I have a capacitor, it's a similar thing. There's an Ohm's law for it. Here's V sub C. Here's I sub C. And I know that I sub C is equal to C times the derivative. That's the Ohm's law, basically, of a capacitor. Yep. All you got to do to approach this problem is I need to know that fact. Once I know that fact, it's basically just using KVL to deal with it. So I'm going to do KVL. So to get the differential equation, what rule do I use here? KVL or KCL? KVL. KVL, right? And so before I do KVL, I always make sure I write my pluses and minuses across that thing, okay? So let me see. This guy here is R1. So I'm going to call that, I call him V sub C, V sub R, right? Biggest problem you guys make in circuits all the time is that you don't go slow when you write the equations, right? You just start writing stuff down, right? If you go slow writing the equations, it's a very easy class, right? You just got to go slow and thoughtfully when you write the equations. So in this case, when I say go slow and thoughtful, that means I'm going to do my KVL like this. I'm going to say KVL is 0 equals what? So what I do is I start here in this corner always, and I just go in a loop like that back to where I started. All right, so help me out. If I start in this corner, right, how do I write the KVL for this thing? Minus Vs, because I go basically from minus the plus on that voltage source, right? And then what? Then I hit the capacitor and I go plus the minus. So if I go plus the minus, how do I write that? Plus Vc, and then I do plus VR because I'm going plus to minus on that. All right, I always do it that way. I'm not putting any Ohm's law stuff in there. I'm not writing down what the voltage source is. I'm just saying the voltage across this element is V something, the voltage across this element is V something, and I basically write it out that way. Because I got multiple, the problem you guys make in circuits is there's possibly as many as 3 different signs that come in with each individual component. And it's real easy to mess it up if you're trying to skip steps in that process. So this is where I should go. You're not ready, most of you, at this point, to skip steps in that process, and you shouldn't. All right. You really should go slow through it. All right. So what do I do here? Now I rearrange it and I say V sub S equals V sub C plus V sub R. Like that. All right. Now what? That's not a differential equation yet. How do I turn that into a differential equation? Be clear, this is my V sub S is that. How do I turn that now into a differential equation? Well, capacitor voltage is V sub C. That's what I'm solving for ultimately. Just to be clear, I'm asking for an equation that's going to help me figure out V sub C. The capacitor voltage is V sub C. How do I write the voltage on the resistor? Current times resistance. So basically I say it's I times the resistance R1. Now, how do I get, I need this to turn into a differential equation. How do I figure out I here? What's true about the I in the voltage source, the capacitor, and the resistor? It's true about the current in all three of those components. It's the same. They're in series with each other. So what I know is that the current in that resistor is related to the voltage on the capacitor with that expression that I gave over here. So I sub C is CdVC dt. If the current in all those things is the same, I plug that thing in there. Now, if you're in circuits 1 right now and you're having a lot of trouble with that, don't beat your head into the wall. All right. Approach me, right? And I'm willing to sit with you and work it out. Don't beat your head on the wall. If you're in circuits 2 right now, I'll help you, obviously, but you should beat your head to the wall a little bit because you should be able to do that. All right. So this is V sub C plus C R dVC dt. All right. At this point, I have now created a differential equation. All right. And the thing that I don't know is V sub C. So let me go to here. So basically, what I've gotten to is Vs equals RC dVC dt plus VC. And I'm solving for V sub C. All right, so V sub S is this voltage source of 4 cosine 2 pi 10t plus phi equals, so yeah, I'll keep going. RC, so it's R1 specifically. So R1 C dVC dt plus V sub C. So let's discuss this a little bit and go back to the problem statement. So basically I said, so write the differential equation for the voltage once the switch closes. Okay, I did that. That is the differential equation. Now, R1 and C, if I put those together, I believe the R1 and C together, what's that? What is R1? What's 1,000 times 0.001? It's 10 to the third times 10 to the minus third. What's that? 1. Okay. So the way that I write this is I'll plug in the values. This guy is 4 cosine 2 pi 10t plus phi equals tau dVC dt plus V sub C. And my tau is equal to R1C, which is in this case 1 second. All right. That's our differential equation at this point. How do I figure out, in general, I know that V sub C, the voltage on that capacitor always has 2 components, right? What are the 2 components to that voltage on the capacitor over time? It's just a differential equation. So normally we would say dy by dt plus y, right? We would say something like that. In this case, y is the output is the voltage on the capacitor. The input is this voltage source. Okay. In this case, so when I talk about the differential equation result, it's got 2 parts. What are the 2 parts always? So the differential equation result, I got the what and the what? Particular or steady state, and then the homogeneous or transient. Okay. And what's the transient always? What form does the transient solution always have? Exponential, right? Always. In this case, what's the steady state going to be? It's going to be a cosine. right? And so if we want to figure out what the steady state's going to be, we guess a cosine where we don't know the amplitude and we don't know the phase, right? And then we solve for it, right? So in this particular problem, what I do is I say solve for the steady state solution of the differential equation, assuming phi is 0, to make things easy. So basically it becomes 4 cosine 2 pi 10t equals tau dvc dt plus v sub c. Yep.
So more to physics 2 would be very well being exponential. We can get into now and talk about aspect of that.
Yeah, so are you in circuits 1 right now or circuits 2? Circuits 1, yeah, it's exactly the same thing. So the reason why, if I have so just to catch, it's a good question, right? So in physics 2, when you're learning about a capacitor, you think about the voltage on the capacitor decaying exponentially over time. It's basically because of that I equals C dV dt. It means that anytime I have a circuit with an R and a C, it's going to be a first order differential equation that's going to end up being what comes out of KVL, right? So yes, it's exactly that. And so the transient response for the voltage on a capacitor is always going to be an exponential that decays. Always, right? And we can talk more about that if you got more questions. If you're in circuits 1, and you feel like you really need to know more, I'm happy to talk with you guys about that. Okay. And even maybe have an extra session for those people just to make sure. If you really don't get it, I'll give you the equation. All right. I get that, right? I know that it's not prereq. I'll give it to you if you have to, but I want to push you a little bit to try it because I think you guys know enough to figure it out. Okay. All right. So the transient response is, so if I said to you, okay, let's just write that out. V sub c of t is going to be equal to the particular solution plus, I'll say a e to the negative t over tau. Right? How do I know it's going to be the a e to the negative t over tau? Well, I would have guessed that the transient response, I'll call it V transient, is equal to a e to the st. Right? You would guess that, you'd plug it into here. Right? When I guess the transient response is a e to the st, I don't plug it directly into that equation, right? What do I make it? What change do I make to that equation when I plug this in as a guess for my transient? What change do I make? I don't plug it in directly to that equation, right? I make one change, don't I? What? I set the equation equal to 0, right? I solve the homogeneous equation that's associated with this thing. And if I did that, what value would I find for S? If I plug this into here, what value would I find for S? What value would I end up with? What does happen if I plug that in? Right? Wouldn't I end up with, 0 equals tau dvc dt plus vc. I plug that into here, into the homogeneous equation, and I end up with an expression, right? That's S tau plus 1 times a e to the st equals 0. And then what do I know S has to be? Negative 1 over tau, right? I'm telling you guys not to skip steps, and here I go doing it, right? Yeah, because I've done it a lot of times, right? You haven't, so you shouldn't skip steps. All right. So I get S equals negative 1 over tau. So that tells me that my transient response looks like that. Tau in this case is 1 second. All right. And so the particular solution, if the input to this thing is a cosine, the output is a cosine. So how should I write that here? 4 cosine 2 pi 10t. What is my guess? So I guess, right? I guess V sub Vp equals what? How would I write that? How would I write my guess? What's the frequency of, so I'm going to guess a cosine, right? Hopefully we're all agreed on that. What's the frequency of the cosine? 2 pi 10t has to have the same frequency. And I'm saying, I don't know what the angle is, and I don't know what the magnitude is. I'm gonna write it that way. So the way we approach this problem is I said, well, that's the same thing as the real part of b e to the j 2 pi 10t plus phi. All right. And we said that I rewrite that as how? How do I rewrite that thing? How do I rewrite this real part of what? How do I break that part up? Yep. I bring the e to the j phi out. Now I realize I'm kind of doing two things at once here, where I'm breaking up the exponential and then I move the e to the j phi up front. Basically, this guy becomes that static phasor and dynamic phasor thing. Basically, with this approach, what we said is the differential equation, we write it, it was a multi-step process. I basically said, well, I take everything over into the basically this thing I called the dynamic phasor. Right, this whole thing here is the dynamic phasor for me. I basically take the whole equation over into dynamic phasor land. Okay. And so for cosine 2 pi 10t, what's that the real part of? 4 cosine 2 pi 10t is the real part of what? 4 cosine 2 pi 10t is equal to the real part of what thing? 4 times e to the j 2 pi 10t. And that's equal to tau dvc dt plus v sub c, right? And I was guessing that my steady state, and just to be clear, if I'm doing this for the steady state, let's call it that. Let me call this v sub c steady state, and let me call this v sub c steady state. So I'm just dealing with the steady state. So I guessed that v sub c of t was the real part of b e to the j phi e to the j 2 pi 10t. All right. Okay. What do I do with this? Well, what I do is I basically plug that in as my guess. And the thing we said is basically if I do this right, the time-dependent parts all disappear. All right. So basically what I end up doing is I do this just in the dynamic phasor domain, I say 4 e to the j 2 pi 10t is equal to tau d by dt of my guess here. So b e to the j phi e to the j 2 pi 10t plus my guess b e to the j phi times e to the j 2 pi 10t. All right, there we have it. So what happens next? Well, I take the derivative there, right? What happens when I take the derivative of this ugly beast? What is the derivative of that? I multiply the whole thing by 2 pi 10, right? Because b e to the j phi is a constant. First of all, b e to the j phi is a constant number, right? Constant number. It's a complex number with magnitude b, angle phi. All right, so it's a constant. So when I take the derivative, I'm just taking the derivative of a constant times e to the something t. So the derivative of something of a constant times e to the something t, I bring something down. Right, so this guy becomes tau times 2 pi 10 j b e to the j phi, like that. And e to the j 2 pi 10t plus b e to the j phi e to the j 2 pi 10t. Now, Both sides of that equation, all terms have a similar term. What term appears in all three parts of that equation? E to the j 2 pi 10t. So that basically, if they appear everywhere, algebra says I can get rid of them, right? So basically, I'm left with 4 equals tau times, let me write it this way, j tau, and tau is a number. I know it's 1, but I'm leaving it in there because in general it's there. 2 pi 10 plus 1 all times b e to the j phi. Now I did a couple of things at once. What did I do? But I also see that b e to the j phi is in both of those terms. So I pulled it out. I used the distributive property here, and I wrote this thing like that. All right. So now what am I doing? What do I do next? Right. Well, let's solve for b e to the j phi. So basically, I can rewrite that whole thing that I just did. B e to the j phi equals 4 over 1 plus j 2 pi 10 times tau. Right. All I did was rearrange this expression to solve for b e to the j phi. Now, you've done this on the homework. We're going to do it now again. How do I solve? First of all, what am I doing? What do I not know at this point? What are the unknowns? I don't know b and I don't know phi. Right? I don't know the angle and I don't know the magnitude. So how do I solve this thing for the magnitude? How do I solve for the magnitude? Even easier, right? I'm just going to take the magnitude of both sides. Okay. I see where you're right. If I get a division, you start thinking in terms of Euler's form here. What's the magnitude of b e to the j phi? What's the magnitude of b times the magnitude of e to the j phi? I can think of this thing. I know it's confuses you guys. You don't like to see e. It's b angle phi. What's the magnitude of b angle phi? B. Okay. That's equal to the magnitude. This way. Go 2 ways here. The magnitude side. The magnitude of the left is b. What's the magnitude of the right? So it's always magnitude of the top divided by magnitude of the bottom, right? So what's the magnitude of the top? 4. What's the magnitude of the bottom? Yep. Yep. That. Okay. Real part squared plus imaginary part squared. And I know what tau is. Again, it's 1 second. All right. If I do the math on that, say I wrote it down so I didn't have to fumble around here. If I put that in with tau, so I got right up here, tau equals 1 second. So this guy ends up being, if I do the math, 0.0637, very tiny. All right. 0.0637. So 63.7 millivolts is the way I would normally say that. All right. What about the angle side? I take the angle of both sides. What's the angle of B angle phi? Phi. It's easier to think of it probably if I say B e to the j phi, the angle of B e to the j phi is phi. I think of it in polar form. Polar form and exponential are just the same. Right? One looks friendlier probably. Right? The angle of B angle phi is phi. What about the other side, the right side? If I take two complex numbers and I'm dividing them, right? I have a complex number on top, complex number on the bottom. So how do I deal with that? Complex number on top, complex number on bottom. How do I deal with their angles? Yeah, angle of the top minus the angle of the bottom, right? What's the angle of 4? 0. What if it had been -4? What's the angle of -4? 180 or -180, right? Either way, right? Because it's pointing on the negative real axis, right? So the angle of the top is 0 minus the angle of the bottom. How do I write the angle of the bottom? Arctan. Now, normally I got to think about it. I know this guy's in the first quadrant though, right? So it's basically negative arctan of the imaginary part over the real part. So it's just 2 pi 10 tau. So if I do that, it ends up being negative 89 degrees. Okay. So if it's negative 89 degrees, basically I ended up with the steady state solution was the real part of b e to the j phi e to the j 2 pi 10t, right? Which we just found was 0.0637 e to the j negative 89 degrees times e to the j 2 pi 10t. So that becomes a cosine, right? How do I write that cosine? How do I write the cosine here? What's the amplitude of the cosine? 0.0637. 0.0637 cosine 2 pi 10t minus 89 degrees. That's what we end up with, right? So in this part, I say take the amplitude of the result. What's the amplitude of the result? Well, it's just simply 0.0637, right? So we're done with that. That's basically part A of what I gave you, except you would go through all the same steps. The only thing that would be different is your differential equation would be different. Still be a first order differential equation, except your differential equation will be in terms of I. All right, that's the only difference. Right. And so you're not doing anything numeric here. You're going through the process of trying to solve this bad boy in steady state. Not asking you about the transient, right? I'm just asking you to solve for the steady state. Because oftentimes, if you're dealing with most circuits, we don't really care about the transient usually. This is a good example, right? We usually don't care about the transient. Most engineers aren't solving for differential equations most of the time, right? The reason is because the transient doesn't usually matter until it does. This is a case where I'm saying it does. Why? Usually, when it matters is usually a situation like what I'm showing here. A tree falls, right? That's going to cause a transient, and that's a problem because that transient is going to be really big, right? And so I need to understand that. But most of the time, trees aren't falling on wires, right? So I don't usually worry about that. I usually worry about what's happening in the steady state condition. All right, this is a case where I am. All right, so part B here says now we're going to write the code to solve for the current numerically. Okay, so I said copy and paste, so V sub C numerically. All right, to do this, please use the following steps. Determine an appropriate time step delta T. Do this by considering the form of the transient solution and the form of the steady state solution. All right, so we did that already. So we talked ourselves through that, and we did examples of that last time. We did example of that last Thursday. We said that the transient response of this guy, or sorry, the complete response to this thing is the steady state plus the transient. So I want to choose that time step for that delta T in my numeric equation. So how do I do that? All right, so I basically point you back to those two notes, which are both posted. You can go back and look at those as you need to. But basically, I know that V sub C of T is equal to the steady state plus A e to the negative T over tau, where the steady state is apparently 0.0637 cosine 2 pi 10t minus 89 degrees plus A e to the negative T over tau. So I suspect you guys don't remember this in too much detail, but I basically said, okay, I got to think through what the time step is when I solve this differential equation numerically. So what do I need to know? Right. I said once this thing's in the computer, basically it's just a series of points that exist in an array somewhere. Right. So I got to think about, where are the interesting features in the time domain? And when I say interesting, basically meaning once this guy gets to steady state, he's a cosine, right? What controls what that cosine looks like in the time domain? What controls what it looks like on the t-axis? The period, right? So there's the period is one potential. Very interesting. I have no idea. I've never seen Zoom do that. I was recording this before. Sorry about that. All right, takes a second to get this back right. Yeah, I'm sure it's still okay. Still recording. All right. I don't know what that was. All right, so I got two things that matter. Basically, the steady state part, the period determines what it looks like. About the transient, what determines what the transient looks like? The tau, yeah. So usually we say in 5 tau that guy finishes up. Okay. So what I want to make sure of, I really want to get this thing right. What I said before is that I usually want to choose my tau such that my delta t is much smaller than 5 tau. So basically there's the 5 tau part, right? And then there's the period part. Those are the two things. I did it before it can see. Okay. So the period and then 5 tau. So my options are to choose delta t to be much less than the period, or delta t much less than 5 tau. All right, let's unpack that for a second. We talked about that before, but let's just talk about it again. To say much less than means what? Why am I saying I want delta t? If I'm thinking about just the transient, or sorry, just the steady state part, I'm saying I want the time step delta t to be much smaller than the period. What does that mean? Why did I say much smaller than? Well, because I want to make sure I get enough points to be able to see a period nicely. Like if I only chose one point, if my delta t and the period were the same, think about that for a second. My delta t and my period were the same. Would I actually draw a cosine when I drew that thing? Right? If my period, so let's think about it like this, right? So if I have a cosine and it looks like that, and I chose my delta t to be equal to t, that means that I basically would solve for that point, this point, this point. If you were MATLAB and you said plot this vector, which includes these points, what do you think MATLAB is going to plot? Straight line. I've lost the sinusoidalness of that thing. If I want that graph of points, that array of points to look sinusoidal, what should the time step be between those points? How closely spaced should those points in that sine wave be if I want it to look like a sine wave? Well, ideally, they would be infinitesimally close together. Well, that's also not possible, right? Choosing them a period apart is stupid. So I got to choose something that's in between infinitesimally small and stupid. So what's that choice? Well, much smaller than the period. So what did I say that was last time? That's an engineering term we use a lot. Two less than signs means much less than. What's a good choice for much less than? Yeah, like a factor of 100. And again, it's arbitrary. Maybe in some cases a factor of 10. But that means that the delta t I'm choosing is 1% of the period, which means that the points are separated by 1% of a period, which means I'm going to see 100 points in one period. So it's probably going to look like a nice, decent cosine. All right, again, there's a theory behind that called the Nyquist sampling theorem that we use to choose, which has some theoretical things, but basically the concept should make sense, right? I want to make sure that I got enough points in there so it looks right. All right, so basically I say my delta t should be much less than the period. So basically the way I often do that is my delta t should be less than t over 100. Now, how do I deal with this one? I said delta t much less than 5 tau. That means I see most of the transient period, and I should have a pretty small spacing between the points in that thing. So I'm going to say my delta t should be less than 5 tau over 100. Okay. Okay, so I got to look at both of them and see which one matters more, which one's smaller. I always choose the smaller of the two. Okay. Why the smaller of the two? Why not choose the bigger one? Yeah. Won't account for the other one. Yeah. So I always want to choose the smallest, right? So in this case, I plug in my t. What's my t? It's my t. So my frequency is 2 pi 10, which is 2 pi over t. So t is 0.1, right? 1/10. Right. And so I end up with here, what do I end up with? This ends up with, this ends up being 0.1 divided by 100, right? Based on the numbers that I have, or 0.001. And then this guy over here, if I plug in the numbers, my tau is 1 second. So this becomes 5 over 100, or 0.05 seconds. All right, so which one's smaller? 0.001 or 0.05? 0.001, all right? So this is my choice. All right, that's our choice. Now, in your report, I would want to see you basically put some, not to do the slop that I just did. I want some words written down here, right? So you'd analyze both of them and you'd say, well, because, I have to choose the smaller of the two, so I chose this one. So, right, so it's words time. All right, this is something you could, again, as I said, you can type it up, you can write it down neatly. All right, I'm fine with either. Okay. The reason I say write it down neatly as opposed to typing it out, this is an example, right? Because I actually would like to see this analysis written out. And writing that out in Word, that's not probably easy for you guys to do, right? And so it's this is the kind of thing where I think you're saving yourself time if you write it neatly. I do say write neatly, not like, you're writing a ransom note or whatever, like you guys do on your exams oftentimes, right? Like I'd like you like neatly on paper, like you took your time to do it. Okay. And I will give you an example that I'll post, which shows, I think for this problem specifically, where I actually write out how I did it. All right. All right. The second part of this thing says, determine an appropriate end time for my simulation. Your graph must show at least 2 complete periods of the steady state and at least 7 tau. All right. So at least 2 complete periods. So 2 complete periods. Basically it's saying I got 2 choices here. I can run this thing for 2 periods or 7 tau, whichever one is longer, right? Whichever one is longer. In other words, because I want to see both the 2 periods and I want to see 7 time constants. I want to see the entire, so I did 7 time constants. I go a little bit past the 5 time constants, right? So my 2 choices for end time, right? So choices for end time. Choice one is apparently 2t, which is 2 times 0.1 seconds, or 0.2 seconds. And choice 2 is apparently 7 tau. Tau was 1 second, so that's 7 seconds. So which one do I choose? 7 tau. Okay. So we said previously, my delta t, I ended up choosing 0.001 seconds. Right? So my delta t is 0.001 seconds. So in my code, I would define a variable delta t and I would call it 0.001. And then I would say my time vector is going to be what? How would I write my time vector? Start at time t equal to 0, right? Increment in steps of what? Delta t. And end where? 7. Okay, 7 tau, right? 7 seconds. Right, that's going to be my time vector I'm going to make. All right, part C, write a MATLAB script that solves for the voltage when after t equals 0. Assume that the initial condition is 0 and that phi equals 0. All right. So we wrote the differential equation. We had 4 cosine 2 pi 10t equals tau dvc dt plus vc. Now what I'm saying is I want you to solve this thing numerically, right? So what did we do to solve this thing numerically? What was the trick to it? How did we solve this thing numerically? Well, we went back to the fact that we said the limit is delta t goes to 0 of y of t plus delta t minus y of t all over delta t is equal to dy by dt, Newton's definition of a derivative. What do I do instead when I try to do this thing numerically? Instead of using this exact definition of the derivative, what do I do? I assume my delta t is small enough, right, that I don't need the limit, right? And I basically say this thing is tau times v sub c of t plus delta t minus v sub c of t all over delta t plus v sub c of t. Like that. Okay. So how did I approach this thing? Once I had this, okay, this looks intimidating when I write this thing down, right? But it's not really that intimidating, right? What do I do? What do I solve for? Well, I basically think of this thing as I solve for v sub c of t plus delta t, which is going to be a function of two things I know, v sub c of t, and my source voltage, which is 4 cosine 2 pi 10t. Right? So it ends up, I mean, you basically you do this thing algebraically, right? And you end up, and I'm not going to go through this part because you should be able to walk through this. But it basically ends up looking like this. I say v sub c of t plus delta t equals a constant times vs of t. So when I say vs, and the source, so 4 cosine 2 pi 10t, like that, plus some other constant times v sub c of t, right? I end up with that. And you can figure out what A and B are. They basically are constants that are in terms of the delta t and the tau, all right? Both of which are known numbers, okay? They're not variables. So, and we often write this, we said, is as, you know, we'll say v sub c of n is equal to A times v source of n plus B times v sub c of n. And my v, this guy is 2 pi, sorry, 4 cosine 2 pi 10 t. I don't want to confuse that, right? It's the voltage source vector, all right, like that. Okay, so the voltage, so v sub c of n at plus 1. All right, in words it says in the v sub c vector, the next value always depends on the current value of the input, which is v sub s, and the current value of the output, which is the capacitor voltage. Okay, so we write a for loop to solve for that. Okay, so I'm gonna I want to do the next part of the problem. This is ultimately the code that I write for parts A and B, right? So this essentially is here my code. So I plugged in my A and my B. You guys can look at this carefully, right, and see what that code looks like. Now, one thing might throw you off, the delta t that I chose is actually 0.1 divided by 1,000. That's different than what I chose in when I solve for it, but it's okay because I can choose a smaller value. I can keep going smaller, right? I can't go bigger. And so I chose a smaller value. All right, so let's jump into part C. I'll post it with the code. You can go through it. Part C basically says, all right, And actually, but just to be clear, what's the rest of that part? Basically, what I asked you to do, write a MATLAB script that solves for it. So basically, you would show me, right, that how you got to those equations that you put in MATLAB. You give me your code that's commented, and then you basically in your report give me a plot, right, and include your commented code. And again, I'll give you an example where you can see, so you guys have kind of a template to follow for that. All right. So the last part here, part C. I'm going to determine the impact of phi, because in reality, what I said was for this circuit, that I had this thing right here. I said the source is actually plus phi like that. Okay. And I want to investigate its impact. So what I end up doing here is I say, okay, we'll write the differential equation for the current before the switch closes and assume phi equals 90 degrees. So the voltage is this. And I didn't change that from the problem. So it's actually 4 cosine 2 pi 10t plus phi. All right. So I want to solve for the steady state voltage. Right. All right. I want to determine the steady state voltage. I say before the switch closes. All right. So this is an important one. Before the switch closes, what is it before the switch closes? What's the differential equation before the switch closes? Yep. Almost the same. What's the only thing that's different here? There's 2 resistors that are basically in series with each other now, right? There's no current that can go down this path. All right. So basically, if you go back to the other equation, the only thing that's changed, the only thing that's different, before I had a voltage source, a resistor, and a capacitor in series. Now I got a voltage source, capacitor, and 2 resistors. If I have 2 resistors in series, how can I rewrite that? One plus the other. So basically, it becomes 4 cosine 2 pi 10t plus 90 degrees equals R1 plus R2 times C times dV c dt plus V sub C. Just that. Okay. Pretty simple. Now, second part, solve for the steady state solution of the differential equation. All right. So my differential equation was 4 cosine 2 pi 10t plus 90 degrees equals R1 plus R2 times C dV c dt plus V sub C, right? This basically, this guy here is like a tau again, right? So same form of the differential equation. That means the steady state, this guy is V sub C is equal to a steady state plus some transient, which is going to be, in this case, e to the negative t over a different tau, the same sort of thing. I said the only thing I care about is the steady state solution. So what's the steady state solution to this thing? We don't have time, and I don't want to go through this in gory detail. What is the steady state solution to this thing? What's its form? Well, if I have a voltage source that's a sinusoidal input, what's my output? Yep, my V sub C steady state is going to be B cosine 2 pi 10t, so same frequency, but I don't know its phase, and I ask you to solve for it. And I think I call it that specifically, right? So you plug that in, you do the same approach that I did before, and I end up with a number when I go through that. The number that I end up with in this particular case is going to be V equals 6.3 times 10 to the minus 4th. And my angle is basically 5V is just about 0 degrees is what I'm going to find out. Okay. I'm not going to go through the solution. That's the same process. All right. I'll post it. All right. In what I post, but enough of that. You guys get the basic idea. So what I ask then is, all right, so using my result from the previous part, C dot B, to determine the initial condition V sub C of 0. Right? What am I asking? I'm asking you to solve for the initial condition. Well, at t equal to 0, what's happening in this setup? What's happening when t equals 0? The switch closes. So what I just solved for was the differential equation before the switch closes. So at time t equal to 0, I would take, so what I said was before the switch closes, I have V sub C steady state. Well, and I'm in steady state. That's the important thing. I'm in steady state at that point. So my total voltage, right? V sub C and the steady state should be equal to each other because I'm in steady state before the switch closes. And I said that was 6.3 times 10 to the minus fourth cosine 2 pi 10 t plus 0 degrees. So I want to solve for what's V sub C of 0. Well, what is it? Well, it basically ends up being 6.3 times 10 to the minus 4, like that. Okay. So I get what my initial condition value is when I do that, right? So what I then ask you to do, right, is I say, okay, now rerun your simulation with phi equal to 90 degrees and my new initial condition. So all I did was rerun the whole thing again, right? So this is for that part here. So basically it's running that thing again. Here's the results that I get. All right, this was with the phi in the source equal to 0 degrees. This is with the phi equal to 90 degrees. Okay. If I go to steady state over here, all right, the steady state on these two guys, maybe unfortunately I should have made my scales different. The steady state amplitude here, this is just about 0.06. This guy also looks like he's 0.06, right? In other words, the steady state values here are the same. So on both of these, steady state is the same in both graphs. Why is the transient so different? Back here, it doesn't even look like it's transient. A little bit, I can see a little bit. Why does it look so different? You're going to see something probably that's very similar to this when you run your simulation in part B. All right, now it looks like that in part C. Why is it so different? What made it change? In other words, both of these are both of these are e to the negative t over tau plus the steady state solution. Same steady state solution. The transient's wildly different. Why? What's that? Oh, somebody said? Somebody. Why does the transient look so different? Well, because of the phase shift. What did the phase shift change? Change the initial condition wildly. Right? The initial condition was 0 in the first case. Second time it was different. So the capacitor voltage always has to stay continuous. Right? So to deal with that, basically the capacitor voltage started out at a much higher value in this case than it did in this case. Right? So it looks like there's a transient here and not one there. There is in both cases. In this case, the transient is being small because that basically that coefficient A in the AE to the negative T over tau is really small. So what this says is basically the initial condition can matter a lot. So when I talk about the problem I have where a tree falls on that line, right? So when I had a tree that fell here, basically what I'm saying is it matters when the tree falls. Does the tree fall when the voltage source is peaking or near a zero cross? It depends, right? If it happens near, in one of those conditions, the transient can be a lot worse, right? And that has a lot of, for reasons we don't need to get into, that has a lot of implications when it comes to the way the breaker itself is behaving, all right? Because the breaker needs to be selected to deal with that large transient. All right, so this is the type of thing that you would do a lot of analysis with in simulation, because again, like I said, you don't really know what those values LS and RS are, and it's kind of annoying because also the transient clearly depends on what the initial condition is. But usually I got to run a number of simulations. We get in the real world, you don't usually solve a differential equation like this in one condition for one set of values. Usually you're kind of doing it over a range of different values. It's easy for a computer to script it and say, all right, we'll run all these different conditions and show me all the different results. So it's kind of again, typical real world example. This should be really similar to what you have in problem 1. So hopefully this will help you guys.